The problem from GATE Physics 2022 paper reads as follows. For an op-amp based negative feedback non-inverting amplifier, which of the following statements are true? Option 1, closed loop gain is less than open loop gain. Option 2, closed loop bandwidth is less than open loop bandwidth. Option 3, closed loop input impedance is greater than open loop input impedance. Option 4, closed loop output impedance is less than open loop output impedance. This is a multiple choice questions where more than one options can be correct, and we have to identify the correct options. Now, just look carefully at the question. So what it's asking us to compare the op-amp in two configurations. That's closed loop and open loop. So open loop configurations are when there is no feedback. So let's say this is our operational amplifier with non-inverting and inverting terminal, and this is the output. Let's say the gain of this amplifier is A. So we can calculate the gain of this amplifier, the bandwidth, input impedance, and output impedance. Everything can be calculated. Similarly, when the same operational amplifier is used using a negative feedback. So negative feedback means this is the output, and the output is being fed to the negative terminal here, like this, using some circuit, resistors in this case, and we have the input here. So this is this configuration, and the input was here also. So again, the open loop gain remains A, but the closed loop gain will change, and we can derive that closed loop gain, bandwidth, output impedance, input impedance can all be derived, and those values will go under a slight change. So we are being asked to compare those values. So the four parameters that we need to care about are the gain, the bandwidth, the input impedance, and the output impedance. Now, the problem asks us to analyze a non-inverting negative feedback amplifier. So we have drawn a circuit for this here, where the feedback circuit consists of this feedback resistor R2, and R2 and R1 combined provide a pathway for the current to flow from the output to the ground here. The input is Vin, which is being provided to the non-inverting terminal here, and we can assume that the open loop gain for this amplifier is capital A. Now note that this circuit can be represented using this generic the feedback circuit that we usually encounter. So we're doing nothing here. So the input is still V in here. The open loop gain is still A, which is being represented here. The only thing that we have changed is that this circuitry in your bottom half, comprising of R1 and R2 resistors, is now being represented by a singular factor named B, the feedback factor, you can call it, feedback gain. So but the other parameters remain the same. For instance, let's see the value of V sum here. So the value of V sum, so let's first calculate the value of this signal here. This signal would be B times V out, and consequently V sum would be V in minus, note the minus sign here, minus B times V out. Correct. Now let's analyze this circuit again. So what we can say, so let's again see the input that is here. So let's call this potential difference VE. So VE we can write as V in, which is the signal here, minus, note that this is V out, and this is a potential divider. So the potential here would be V out times R1 over R1 plus R2. Now note that this is the input to the input here, what we're calling V sum, and VE are effectively the same. So VE is nothing but V sum. Now if we compare these two parameters, we can clearly say that A is the open loop gain for both, which is pretty evident, self-evident. However, the factor B, which we saw the feedback factor here, by comparison we can say that the feedback factor B is nothing but R1 over R1 plus R2. So this is the information that we gain, and we have established that this circuit, the non-inverting negative feedback circuit, can be represented using a generic feedback configuration. Now let's talk a bit more about this feedback configuration. Now note that the output, we are shunting the output. So we are effectively taking whatever the voltage is and feeding it to our feedback network here. So this configuration where the output is fed, where the output voltage is fed to the feedback network, is known as the shunt configuration. So on the output side, we have a shunt configuration because it's sort of a parallel. So whatever output voltage we are getting, we are directly feeding it to the feedback network. However, on the input side to this operational amplifier, we are putting the output voltage in series. Note that we are not directly feeding the result of this feedback network to our operation amplifier. No, we are providing the result of this feedback network in series to another signal V in here. So note this formula, V in minus VB out. So we are doing effectively, we are adding or subtracting the 2 voltage in this case, which means that on the left side, on the input side of this op amp, we have a configuration known as series configuration. Why series? Because the voltages are being added or subtracted, because it's a negative sign, it's a negative feedback. So here they are subtracted, they are in series. However, on the output side, the output voltage directly being fed to the feedback network. Hence, this is called a shunt configuration on the output side, and it's a series configuration on the input side. This is what we have written here. It's a series shunt configuration. The nomenclature is, we write first the input side, which is series here, then we write the output side, which is shunt here, and configuration. Now now in the series shunt configuration, what we can do is that we can derive these formulas. So let's say in the open loop, the gain is A, bandwidth is F, input impedance is Zin, and output impedance is Zout. However, in the closed loop, what happens is that gain gets reduced by a factor of 1 by AB. Note that the gain is being divided by 1. So typically the open loop gain is 10 to the power 5 that we encounter. So however, in closed loop, the gain is heavily reduced by 1 plus AB factor. However, the bandwidth increases by a factor of 1 plus AB. Remember a golden rule for operation. For a given amplifier, gain into bandwidth equal to constant. So if the gain is reducing when we are going from open loop to closed loop, correspondingly, the frequency or the bandwidth will increase, which is happening. Note that the product here would be A times F. Again, the product here, the gain into bandwidth product would be A into F, because 1 by AB will get cancelled out in the numerator and denominator, right? Similarly, input impedance, since the input impedance is in series, and we know that series resistances add up. So what's happening here is that the Zn would increase by a factor of 1 plus AB. So the open loop configuration, the open loop input impedance was Zn, but since the input size is a series configuration, so the input impedance for the feedbacks for the closed loop circuit will increase by a factor of 1 plus AB. This is very similar to saying that you have a resistance 1K and then you add another resistance in series of 1K. So the total resistance would be 1 plus 1K, that will be 2K. Similar thing is happening here. So original open loop input impedance was Zn. However, due to closed loop, another factor of Zn times AB got added, and hence the input impedance increases since they are in series. The reverse thing happens in parallel. Let's say you have a resistor 1K and in parallel you apply another resistor 1K. So what is the effective resistance? The R effective would be 1 into 1 over 1 plus 1, that's 0.5K. So the resistance reduces, and in the output side we have shunt. It's equivalent to a parallel circuit. So the output impedance, if originally it was Z out, now it should reduce. Note that the effective resistance should reduce when they are in parallel. So they are in parallel here, the feedback and the open loop configuration. So the output impedance will decrease by a factor of 1 plus AB. So now we have established that while going from open loop to closed loop, gain decreases. So gain decreases. So we know that the open loop gain is A. However, closed loop gain is A upon 1 plus AB, while open loop gain is A. And so this is obviously greater. So option A is correct. Now we know closed loop bandwidth is F times 1 plus AB. However, open loop bandwidth is F. So this option is not correct because 1 plus AB will always be a factor that will be greater than 1. A and B are positive quantities, please note that. So 1 plus AB will always be greater than 1, and closed loop bandwidth will always be greater than open loop bandwidth. So option B is incorrect. Now closed loop, open loop input impedance is Zn, and closed loop input impedance is Zn times 1 plus AB. Because input size is series, and in series the resistances add up, so the closed loop input impedance will always be greater than open loop input impedance. So option C is correct. Now option D, closed loop output impedance, open loop output impedance is Z out. However, closed loop output impedance is Z out times, divided by 1 plus AB. Why is this so? Because on the output side we have a parallel connection, and when we have parallel connection, effective resistance or effective impedance decreases. It decreases by a factor of 1 plus AB here. So open loop output impedance will always be greater than closed loop output impedance. So option D is also correct. Now, in this question we were required to find out the correct option. So we have three correct options here, namely A, C and D, based on the parameters of gain, bandwidth, input and output impedances of a negative feedback non-inverting amplifier while comparing the open loop and closed loop configurations. Thank you for listening.